Good evening, everyone. I welcome you all to the fourth live session of the NPTEL course, Production Technology Theory and Practice. The tutor for this particular course is Professor Shona Kumar Chaudhary from IIT Kanpur, and I, Arnab, am the teaching assistant for this particular course in this cycle. So, last week's video lectures were mostly pertaining to machining operation and the basics of turning. So we have come across the terminology orthogonal machining and oblique machining and the basic and the fundamental differences between them. We also have encountered few numericals. So today's live session will be encircled around a few of the numericals that I have taken from previous year's assignment questions and a few that I have formulated myself. Coming to the first question. Okay, coming to the first question. A mild steel workpiece is being machined with a tool with which is having the following tool signature. So in the last live session, we have already discussed about the different tool signatures and also how we can convert from one signature to another signature for getting the different values of the angles. So the question is asking if the average value of the coefficient of friction between the chip and the tool is 0.5. So we have got mu. And this is actually the apparent coefficient of friction, so I am denoting it by mu a 0.5. Then what will be the value of the shear plane angle? So you are not having any information on the chip, that is the chip thickness before being cut, that is uncut chip thickness, or after being chopped off. So we are not having the value of A1, A2. More particularly, we are not having the value of chip reduction coefficient zeta. So we already know this particular relation for shear plane angle. So we can't apply, like we can't really use this equation here because we don't know the value of r. R is nothing but 1 by A2. So since we don't know the value of r, so we have to think the problem in a different way. We know that there are two relations for which can be used in case we are not having these values. One is Einstein-Merchant's equation. We have already encountered this in the last couple of videos. And the second is Lee-Schaffer's equation. So both of these equations are based on minimizing the power requirement. So if we minimize the power required, that is if we differentiate it with respect to the shear plane angle beta naught and equate it to 0, since P is P min, minimum power, and also we know that we can write power as cutting force, which is Pz into cutting velocity Vc. So Vc here is constant. Pz will vary if beta naught varies, right? So beta naught is nothing but the shear plane. Suppose this is the material, this is the tool attacking the material here. This is the uncut layer of the material. This is the chip that is getting separated out after the turning operation has happened, or the machining operation has happened. This is gamma naught, that is the orthogonal rake angle. This particular angle here, along which the shearing is occurring. So this plane we call as shear plane, and this angle is beta naught, or the shear plane angle. So cutting velocity is the velocity the relative velocity between the tool and the workpiece. So there are other components of power also due to the feed motion and the force along that direction, but we can neglect this conveniently with respect to the value of since the value of Vc is quite larger than Vf, and also Pz is greater than Px. So with these assumptions, this particular term can be neglected, and all we are left with is Pz into Vc. So Pz is the only variable here. So if we can write it as dPz by d beta naught equal to 0, and we already know the expression for Pz. You can derive it from the Morse circle, sorry, from the merchant circle, or you can also remember it, whatever is convenient for you. So yeah, now this term As can be written as the area of the shear plane. This can be written as S naught into T divided by sine beta naught. This we have already derived in the last class, how it is coming. So this is also a function of beta naught, right? So we can see the beta naught terms are appearing here and here also. So if we substitute the value here, then we are left out with nothing but so I'm not writing the expression again. I can simply rewrite this as we want to maximize the denominator so that the Pz becomes minimum and thereby the power consumption also becomes minimum. So what is the denominator here? Denominator is sine beta naught, which is coming from this As into cos beta naught plus eta minus gamma naught. Beta naught is the shear plane angle, the eta is the friction angle, gamma naught is the orthogonal rake angle. So yeah, then if you proceed with this particular differentiation and equate it to 0, you will arrive at an equation to beta naught plus eta minus gamma naught is equal to 0, which is nothing but the Einstein-Merchant's equation. So this is just the basic derivation. My aim here was not to just solve the numerical and go. I just wanted to show how you arrive at this particular equation. And similarly, but there's a problem with this. Here we are assuming that this tau s, it is constant throughout this entire process. But in actual machining operation, tau s is not constant. Not constant with respect to beta naught. So and other parameters also. How I am telling. So we know that due to thermal softening of the material, tau s varies. The shear strength of the material varies, and also due to strain hardening, the material gets hardened, and the tau s increases. So these are two complementary effects. I mean, two contradictory effects. So, from that we can write tau s as a function of as a linear function of the normal stress that is getting imposed on the workpiece material along this shear plane. So it can be written as tau naught, which is a constant, plus k, which is another constant, into sigma n. This is the normal stress. Normal stress is nothing but the normal force Pn divided by the shear plane area As. Okay. Now we can rewrite this sigma n terms in this manner. Like if we draw the merchant circle and again derive this Pn from there, there will be a sine term here, and This AS will get cancelled out, and I think a sine term here. I'm not going into the details of that. You can try it out by yourself. Then if you again differentiate it in the same manner with the aim of minimizing the power, you will arrive at an equation which will be somewhat like this: beta naught plus eta minus gamma naught is equal to a constant, say k dash. Okay, so you'll arrive at an equation like this. Now this constant k, you need to know to get the angular value. So that's why, by applying the slip line theory and by drawing the Morse circle at this particular region for the planes such as this shear plane, this is the primary shear plane, there's another secondary shear plane over here, and the plane along which the value of stress is 0, that is where the chip is getting detached from the tool surface. So there the stress value will be 0, both shear stress and normal stress value will be 0. So with these informations we um, draw a Morse circle, and from there we derive the different values of angles, and from there we arrive at the Lee Schaeffer's at the equation, which is nothing but beta naught plus eta minus gamma naught is equal to pi by 4, which is popularly known as the Lee Schaeffer's equation. So you have two equations at your disposal. You can use any of them, but as you are using, you should write that we are, by assuming this particular scenario, we are using this particular equation. So these are the two equations. Another thing here, the tool signature that has been given is in American Standard System, right? But the value of, so you know eta here, it is friction angle. You have been given mu is equal to 0.5. So eta is nothing but tan inverse of 0.5. Gamma naught you have to calculate. How you have to calculate? You have to first convert this ASA to ORS. That is the orthogonal rake system. Since the machining is happening in orthogonal plane, so you have all the angles in the orthogonal plane. So you need to find out gamma naught from gamma x, gamma y, and the principal cutting edge angle, right? So you have the expression here: tan gamma naught is equal to sin phi tan gamma x plus cos phi tan gamma y. So what is phi here? Phi is 72.5 degree, right? This is the principal cutting edge angle. 13 degree is the auxiliary cutting edge angle. Okay, this is gamma y, this is gamma x, this phi e, this is phi s. So from there you have to find phi. Phi is nothing but, this is the side cutting edge angle. 90 degree minus phi s will give you the principal cutting edge angle. So if this is your tool, from the top view on the machining plane, if you are seeing, then this angle is phi s, this angle is phi, this angle is phi e. So 90 minus phi s will give you 17.5 degrees. Yeah, now you have all the values. You have gamma x, you have gamma y from here, and you also have phi. So from here you will get gamma naught is equal to 6.22 degrees. Okay, so if you plug in the values, you will just get it. Now you can use any one of the equations. By using Ernst and Merchant's equation, you will get a get the value of beta naught is equal to around 34.825 degrees, or 35 you can approximate it as 35 degrees. So this is the answer that has been given in the solution. Similarly, there's no mistake if you apply the Lee-Schaeffer's formula also. You will arrive at a less value of beta naught, which is, so I have no place to write here. I'm just erasing this part and writing. So applying Lee-Schaeffer's equation, we will get beta naught is equal to 24.65 degrees. Yeah. So this is how you should approach this problem. See, these derivations I just did to make few things clear how we are arriving at these two particular equations. Otherwise, you may feel that from where these equations are coming from. Okay. Going to the next numerical. For turning of a rod of 20 mm diameter rotating at 1000 rpm, the feed was given as 0.1 millimeter per revolution and the depth of cut was 1 mm. Find the material removal rate for this operation. So it is a pretty straightforward question where you have been given n is equal to 1000 rpm, feed rate as 0.1 millimeter per revolution, depth of cut as 1 mm, and the diameter of the rod as 20 mm. You have to take care that about the units as well as this diameter, whether it is written as diameter or radius, and accordingly you have to substitute the values. So you know MRR for turning operation. So this is my feed velocity S naught. This is the depth of cut that I am providing during the machining operation, and this is the rotational velocity or angular velocity. We know MRR is equal to cutting velocity Vc into S naught into T, right? So the feed S naught is how much the tool is moving in the lateral direction in one revolution. As the workpiece is revolving by one revolution, that is by 360 degree, how much the tool has moved along the feed direction. Suppose after one revolution, this is the position of the tool. Then this particular distance is nothing but 1 mm, sorry, 0.1 mm in this particular case. Feed. This is S naught. So likewise, in 1 minute, the workpiece is rotating 1000 revolutions. That is 1000 into 360 degrees in 1 minute. So how much is the tool moving in 1 minute? It should be S naught into N, right? So S naught into N is how much the tool is moving in the lateral direction. So yeah, so what is VC here? VC is nothing but pi dn. Here n is in revolution per minute. You have to convert it to second because you have been asked to answer MRR in second, millimeter cube per second. Pi dn by 60 into S naught into T. You plug in the values here. So you will get somewhere around 105 millimeter cube per second. This is a very easy problem, but there's one catch here. In this particular question, you have been given the value of RPM. So this is a single pass problem. I think we have another problem with multi passes. Just let me check. This is also single pass problem. Okay. So yeah, let's leave it here. This is what the question was asking, and we'll move to the next question. So this is the answer, 104.72. I have approximated it to 105 per second, millimeter cube per second. In a shaping operation, cutting speed the cutting speed is 5 meter per minute. Speed is 0.2 mm per stroke, and depth of cut is 0.3 mm in a shaping operation. So as you know how this shaping operation actually looks like. So this is my tool here, shaping tool. This is the slot which we get after sorry. So you have the material which is getting removed here. So this is the motion of the tool, say with a cutting velocity Vc of 5 meter per minute in the perpendicular direction out of the paper, and you have the feed motion that is given to the tool, which will be along this direction. So that is 0.2 mm per stroke. So this motion, it is the forward stroke, this is the backward stroke, cutting operations in the forward stroke, and the tool just retracts without cutting in the backward stroke. So per stroke, which includes this forward and backward motion of the tool, the feed velocity, that is the velocity that is imparted, the displacement that is imparted to the tool along the feed direction is 0.2 mm per stroke, and the depth of cut, it is d is equal to 0.3 mm. So just you have to find out MRR. You're asked to find out the power consumption. So power consumption is nothing but the amount of energy which you are spending to remove unit volume of the material. So that's 10 joules per millimeter cube, which is also known as specific energy, into the amount of material which you're removing per unit time. So ultimately you will be having something like joule per mm cube into mm cube per second, say. So joule per second will give you watt. So like that, this formula is coming. So that material you are removing per unit time is nothing but the material removal rate. We know that the material removal rate is nothing but Vc into Vf into D. Sorry. So in one stroke, you are removing, say, this much material in one stroke. So this is the stroke length from here to here. Say in one stroke it is moving from here to here. So this area is nothing but 0.2 into 0.3, and the velocity with which it is moving along this particular direction is Vc, that is the cutting velocity. So you're multiplying that. So this much amount of material you're removing in 1 second. So it's 10 and 2. We should take care about the units. Take care of the units. So 5 into 1000 millimeter cube. Sorry, millimeter divided by 60. You have to do to convert it to seconds into VF is 0.2. That's already in millimeter. So depth of cut is already also in millimeter. So you'll get somewhere around, I think, 0.6. So 6 by 10. It is around 50 watts. Just cross check. And okay, so one thing. Yeah, so here power is generally we write as Fc into Vc. There's a force into the cutting velocity, the force along the cutting direction and to the cutting velocity. Plus you also have another component, right? Along the feed direction, say that is x direction into feed velocity. So in case of turning operations, this is shaping, but in case of turning operations, you can also approach the problem in this manner. Suppose you know the values of Fc and Vc and also Fx and Vf, then also you can find out power from there. In case you are not given with the values of feed and sorry, you're not given with the values for from which you can calculate us. I mean, the specific energy of the material is not known to you. In that case, you have to find out power from the forces that are given to you. So forces can be measured using, say, for an unknown material, we don't know the value of us, right? We are trying to find out us. So in that case, we are using a dynamometer to calculate the values of Fc and Fx, that is the values of force in different directions, the feed and the cutting direction. And we already know Vc and Vf because we are inputting it. It is an input from our end, input parameter. So we plug those values and we get power. From power, and also we calculate MRR from this Vc Vf values, depth of cut also. And then we calculate Us is equal to power, that is P divided by MRR. This is another type of problem that you may encounter. So in those type of problems, you should be given with the values of cutting forces. Or to be more practical, you need to measure them using a dynamometer. A steel cylindrical job, the next question, a steel cylindrical job of 200 length is being turned at 1000 rpm at 0.1 millimeter per revolution speed. The time taken in minutes to machine the job in one pass. So this is important here. What happens in case of multi-pass turning, that also I will explain. So this is the entire length of the cylinder. So suppose you are starting from here, the turning operation, and this length is given as 200 mm. So we know that as the cylinder is rotating by speed n, and we are making the tool being fed at a rate of 0.1 mm per revolution, which is s naught as a feed, and n is given as 1000 rpm. Then, as I said in the last question, that how much time is it taking to, how much distance it travels in 1 minute along the feed direction. So to calculate that, we need to do S naught into N. So this is millimeter per revolution and this is revolution per minute. We will get how much distance the tool travels in unit time. So if we divide that particular distance, say we are telling as D, the distance it is traveling in unit time, D subscript U. If we divide the total length of the workpiece by du, then for single pass operation, we can find out what is the time taken for machining. Now, if we have been given with multi-pass operation, then we need to just multiply this with the number of passes. Now, you need to take care of one thing here. In this particular problem, you are given with the value of cutting speed in angular velocity, that is n. So n is not dependent on diameter of the workpiece here. Suppose you are telling the machine that you have the spindle is being given an input, sorry, the motor has been given an input to rotate the spindle at a fixed rpm, say 1000 rpm. In that case, whatever be the dia of the workpiece, this is the rpm. So that won't affect the value of t here in subsequent passes, say pass 1, pass 2, pass 3, it won't affect. So you can simply multiply the number of passes with L by S naught N and find out the time of machining. But suppose you are given that the motor, or suppose like in the question you are given with a cutting velocity, say 5 meter per minute, or it can be any values, like this I am taking arbitrarily. So this is rather very small. In turning operations, it's high. So yeah, suppose you have been given with the cutting velocity Vc. I'm not taking any values, just I'm writing Vc. Okay. So in this case, you see that in the first turning, in the first pass, your diameter is d. So you have pi dn by 60, which is equal to Vc. So in the first pass, your diameter is d, right? So accordingly, you will find out n and you will substitute the value here and you will get the time of machining for the first pass, n equal to 1. For the second pass, the diameter of the workpiece has reduced. So now you are left with d minus 2 into t. T is the depth of cut, this much, right? So in this case, what happens? Your diameter is reduced. So for n equal to 2, that is the second pass, your time of machining will also change. Say this one is T1, so this is T2. Here you have to find n by substituting d in place of d. You have to write d minus 2t, and accordingly you are given with the value of Vc. So accordingly you find out n for this particular operation, for this particular pass, and likewise you will carry out the subsequent passes, n equal to 2, n equal to 3, and so on. So every time you have to find out the reduced diameter, and so in this case we have already assumed that Vc is constant, so the n will vary from first pass to second pass. Yeah. Okay. 10 mm hole is being drilled in a mild steel block with 500 revolutions per minute of the drill rotation frequency, so it's angular frequency, and 0.2 millimeter per revolution of drill feed. So you're given with phi is equal to, sorry, d is equal to 10 mm, n is 500 rpm, and drill feed, I think that's f is equal to 0.2 mm per revolution. So drilling operation, if you try to visualize, it's, this is the material that you want to remove from the workpiece, and you have a drilling tool here. Okay, so it is rotating at 500 rpm, and it is coming down at 0.2 millimeter per revolution. Same thing, how much distance is it moving in unit time? To find that out, all you need to do is n into f. So that is the distance that this drill is covering in unit time, or you can say that the feed in time scale, say how much distance I am covering in unit time. If we define feed in that manner, that will be n into this thing, this feed per revolution. So if we just so the velocity vf I am writing, this is vf. So simply if we are multiplying the area with this vf, we will get how much material it is removing in unit time, right? So that is nothing but mr. Pi d square by 4, that is the area of cross section, into vf. So vf is nothing but n into f. So if you are substituting the values, you will get as I think 130.9 millimeter cube per minute. Similarly, you can find out the specific energy which is consumed in the process. So yeah, specific energy consumed in the process is 1.5 joules per millimeter cube. Since we already know the material, so we can conveniently say that the amount of energy which is required for this particular operation, it's 1.5 joules. So what will be the power consumed? So P is the specific energy into MRR. So I think this will come around 3.27 watt. Actually, I'm not calculating this. You just calculate and check. I think okay. Yeah. So this is the last question for today, and yeah, for a turning operation which is done at n equal to 500 rpm, depth of cut 4 mm, feed rate 0.32 mm per revolution, using a tool having the following tool signature. So since it's mm, so this has been given in ORS. The chip thickness was measured out to be, oh, this can also be NRS, right? But since here the first angle, that is lambda, it is given as 0 degree, so both will be same here. So the chip thickness was measured out to be 0.8 mm. This is the chip thickness. After the chip has formed, you measure the thickness, and the dynamometer rate the force components in transverse direction and cutting directions as 200 Newton and 1000 Newton. So you are given that Fy, sorry, it's Fx rather, transverse direction is Fy, longitudinal direction is Fx, and Fz is equal to 1000 Newton. These are the dynamometer data, and you're given A2, which is the cut chip thickness, that is after being cut, 0.8 mm, and also you know gamma naught from the tool signature. You know gamma naught is equal to 12 degrees. Phi is 60 degree, phi 1 is 30 degree. Yeah, these are all the information you know. And since lambda is equal to 0, it is very important to note. So you can assume the particular operation to be orthogonal cutting. So due to the orthogonal cut, the operation being an orthogonal cutting operation, you can draw the Marchant circle diagram and find out the different components of forces here. You also have other 500 RPM as the cutting speed. Depth of cut is 4 mm and speed rate is 0.32 mm per revolution. Okay. So you have to find out the coefficient of friction. So to find out coefficient of friction, we either need to know, see here we can apply the Lee-Shaffer's equation or Ernst-Marchand's equation to calculate coefficient, to calculate the shear angle, and from that shear angle, you first calculate the shear angle. From that shear angle, you can apply Lee-Shaffer's equation and calculate friction angle, and from that you can get mu. That is one approach. But here you can't, you know, uh, deduce the value of shear angle because you are not having A2, sorry, A1, that is the uncut chip thickness. You don't have that. So consequently, you can't find out the value of zeta or r, and hence you can't find out beta naught, that is the shear plane angle. So the only way left out here is the force analysis. Force analysis means you have to find out friction force F and the normal force on the rake surface N, and from there you can find out mu. This is nothing but the apparent coefficient of friction. So for F and N, we need to know at least two sets of forces, that is, one set of forces that can be either Fxy Fz, or it can be shear force and normal force to calculate this. But we know that we are not given with these values, rather we are being asked to find out these values in the question, but we are given out with Fz and one of this Fxy, there is the thrust force components, that is Fy. We can find out Fx by applying this particular equation. So this is my tool. So suppose, sorry, so this particular force Fxy, thrust force, it it is perpendicular to this cutting edge. So we know this value is phi, so we can say that this value is also, this value is also phi, right? This is phi, this is phi, this is 90 minus phi, this is again phi, and this is fx, which is fy. So from here we can write fxy is equal to fy divided by cos phi, right? This is nothing but 400 Newton. If you substitute the values, you will get. Okay. Well, so next you have to construct. So you are now having this one set of forces. Fz, you know, fxy is also known to you. Now you can find out the other force values. How? So you can, for your convenience, you can find out R, that is the resultant force. It is nothing but fxy square plus fz square. So that will come out to be around 1077 point something, 1077 Newtons. Okay. So R we know. If we draw the merchant circle, this is my tool here. Along the rake surface, if we extend the line, we will get the force, friction force vector. Normal to that is the normal to rake face, that force component normal to the rake face, and this is R. So we know that this angle is beta naught, sorry, gamma naught, that is the orthogonal rake angle. And this particular image I am drawing in which plane? This pi naught plane. It is the orthogonal plane. We have fz in this direction, fxy in this direction. What is the other component that we are having? Sorry. So this component should be mutually perpendicular. This fs, fn, then fz, fxy. You know that. So this particular angle, this particular plane along which fs is acting is shear plane, and this angle is shear angle, beta naught. And I'm not drawing a the circle, but just so this will be your merchant circle. Okay. We also know that this particular angle is eta, or the friction angle. If we do a few, so this is also gamma naught. If we do a few calculations, we will find that this particular angle, this is nothing but eta minus gamma naught. Okay. Since this angle is 90°, we know this one, and this is 90 minus eta, so this will be 90 minus 90 minus eta minus gamma naught. So that will give you eta minus gamma naught. This particular angle that R makes with Fz. So now we have to find out F, that is the friction force. So okay, so what other values are we given with, that we need to see first. So yeah, see, if we see this particular triangle, FZ, FXY, and R. This particular triangle, we know this angle. So tan eta minus gamma naught is equal to Fxy by Fz, right? So gamma naught we know, eta we need to calculate. Fxy and Fz we know. So if we substitute the values, so this ratio will come out to be around 0.4. So gamma naught we already know, it's 12 degrees. So from there we will find eta is equal to around 9.801 degrees approximately. Okay. So once we get eta, we can find out mu apparent, that is the apparent coefficient of friction. The apparent coefficient of friction is around tan eta is 9.8, 0.17, 173. So this is the first thing that you have calculated, coefficient of friction. Next is uncut chip thickness. Uncut chip thickness is A1. So you know this particular expression, tan beta naught is equal to okay. So here you don't know beta naught, right? But you can, but you are given with the value of feed and feed rate, I think. Yeah. So you are given with the value of feed rate and depth of cut. Yeah. So from there you, and also you know phi. So from there you can find out the uncut chip thickness. So we know that A1 is S1 S0 sin phi. So that comes out to be around, okay. So this is the uncut chip thickness. From this particular expression, you have calculated uncut chip thickness to be around approximately 0.3 millimeter. So you can note one thing: the chip thickness after cutting it is 0.8 mm. So it is obvious that the chip gets thickened due to this turning operation. So that's why A2 is greater than A1. So the value of R from here you can calculate R is equal to A1 by A2, 277 by 0.8, so 0.346. Okay. Now you know R, you know gamma naught, you can calculate beta naught or the shear plane angle. So beta naught is after substituting these values you will get around 17.539 degrees. Yeah. Why we calculated beta naught? Because if we look at the merchant circle, if we need to calculate Fs and this Fs and Fn, this green colored components, we need to know this particular angle, right? Only then we can relate this R or any other Fz, Fxy with this Fs and Fn. Otherwise, it's not possible. So now it's easy. Now, if you want to calculate, say, Fs, it's nothing but R cos beta naught plus that angle that we have already calculated, eta minus gamma naught. So this will give me around 832.97 Newton. Similarly, if we proceed for Fn, which is the force normal to the shearing area, that's the sine component, will give me 682.75 Newton. So we have got these two forces that we have been asked for, normal and shear components of forces. Now we are asked about the shear strength of the material. So that's also easy. You have the shear force. All you need to do is find out the shear area, Fs by As. So As we already know, it is S naught into T divided by sine beta naught. Beta naught is this shear plane angle. So from there, if we what we're doing is simply like you simply substitute it here, and we'll get tau s as close to 196.11 Newton per mm square. We need to be careful about the units here. This S naught and T are given in mm, so this will be mm square, and Fs is given, it's in Newton. We have got, so 196.11 Newton per millimeter square, or megapascal. This one you also write as megapascal. Okay. So last parameter that you have been asked to calculate is the shear strain. So we already know the formula for shear strain. Gamma, as we are already using to denote rake angle, so I will use G. Say G is not G, sorry. Say I am using epsilon is equal to cot beta naught plus tan beta naught minus gamma naught. If we already know beta naught, we have calculated that. Gamma naught is given in the question. You substitute and you will get it as around 3.731. Is the shear strain. So how this particular expression is coming, I already discussed it in the last class towards the end.